All right. In this last video, we will talk about multiprocessing because this can greatly speed up our workflows. I basically generate a synthetic data set of zeros and ones for a target and then predicted probabilities. And we're just generating 5,000 of these. And then basically what we do after that is that we call the find concordant and discordant ratio and summers D. I'm not going to go too much in depth on what these are. These are topics that you can research on your own time, but this is a model evaluation technique that a data scientist might actually want to apply. So this takes our y-test and our probability predictions and some type of a model ID. The first thing we do is generate a bunch of pairs. So let's look at this function. So this will find the combination of every predicted probability in the negative class and every predicted probability in the positive class. And then, as you can see, this will return a list that is just finding the product of the negative probabilities and the positive probabilities. Again, if you're more interested in what this technique actually is, you can definitely research these terms on your own, but this is mostly just to show multiprocessing. And then really the multiprocessing happens here. And so what do I mean by multiprocessing? I mean that we can take a function and take data and run those across multiple cores and then bring all those results back together and use them. So as you probably know, Python just runs on a single core by default, but we can use this multiprocessing library to say, okay, if I have 8 cores, I can run parts of my operation on each of those 8 and then bring those all back together, and that should save me time. So this is a context manager, so this will ensure that whenever the multiprocessing is done, basically everything gets shut down properly and nothing is left hanging. We can define what function callable we want to apply and then what data we want applied to that function callable. So pairs is just a list. So this is where we pass in our iterable, and this is where we pass in our callable. And this will get spread out across all of our CPU cores. So again, we're more or less under the hood. We're going to be taking chunks of this list called pairs and then running find discordance on each of those chunks, and then that gets concatenated and returned as a list called result. So again, I'm not going too much in depth on what the actual calculation is, but number one, you need to make sure that this is something that can be run in parallel. Certain operations actually are very difficult to run in parallel. This is something to where the rows, I shouldn't say rows, I should say the pairs that we have generated here, the pairs that we have generated, one is independent of the other. So there is no issue with actually running this in parallel. So what does a find discordance do? This finds the number of discordance defined as the number of cases where the predicted probability in the negative class observation is greater than the predicted probability of the positive class observation. So this is just kind of finding instances where the assigned probabilities for the model don't make as much sense as we would hope them to make. So this is called a discordant pair. And so that's what we're finding here. And so we can see that after we get this list, we can kind of then do some operations based on this. In this case, it's actually really pretty simple to find the concordant discordant ratio. We just take 1 minus the discordant pairs divided by the pairs. So pairs, we just say what's the length of the result, and then the discordant pairs are just the sum of the results. Again, I'm not giving a model evaluation video here. More so the focus is on multiprocessing, but if you want to, you can kind of look through these operations and see what happens. But again, this is a quick example of how we can actually use multiprocessing in this case. So let's let this fly, and we can see that, yeah, this ran pretty quickly. and I can look and see, okay, now I have a CSV file of the concordant discordant ratio and then a statistic called Summers D, which is related to this as well. But again, applying multiprocessing is fairly easy. You just have to know what's the callable and then what am I passing into this callable across different cores. So again, if I look at, didn't want to do that, we can see that, this takes pairs. So this can take a set of pairs on core A and a set of pairs on core B and a set of pairs on core C. Now, if we did have other arguments that we needed to pass in here, I don't get into that here, but you can use from func-tools a partial function and call a partial function. So if you needed to pass in a data frame here and subset and do operations on that data frame in parallel, you could do a partial function where you set that data frame object that's in memory as a default argument and pass that into multiprocessing. So there are ways to do that, but this is just a very simplistic example. And again, to do our concordant discordant ratio, we're able to just do some pretty simple operations on this result here, taking the length and doing a sum and all of that type of stuff. So again, we can just see that at the end of the day, discordance is just an integer, more or less. And then, of course, this just writes out our data frame that we saw here. So I hope you found this interesting. Again, multiprocessing can definitely be very powerful, and it's a way where we can definitely speed up a lot of our operations.